The other extremely excellent method at looking using molecular dynamics is to use something called coarse-grained molecular dynamics simulation. And in this case, what we have here is the method where we combine 3 to 4 heavy atoms into one particle. So here, what we have on the right-hand side is a PIP2 lipid, where inositol rings turns into 3 beads, oops, and a phosphate turns to 1 bead, and glycerol head turn to 1 bead each. And this is palmitoyl oleo, so about 16, 18 carbon turn to 5 and 4 beads. What this allows us to do is that this is much cheaper to run than a normal atomistic. So as we say, we have to integrate it over time step, right? In atomistic, we integrate it over 2 femtosecond time step, where in coarse grain, we do it over 20 femtosecond time step. Now, very importantly, when we discuss molecular simulation of atomistic system, we have to solvate the box with water, right? And now there's quite a lot of particles of water in the box. Here, what we do is that we ignore the hydrogens because it's a heavy atom, so we just take oxygen, and 4 waters turn to 1. So we have a much less water particle. So it is much cheaper to run coarse-grained molecular dynamic simulation. And an interaction, we are using 10 scales interaction, Martini 2, Martini 3 is coming out very soon as well. And the secondary and tertiary structures of a protein, as you can imagine, we scale and grouping these things into beads. The interaction is not going to be as accurate as atomistic. So you might see some proteins starting to lose secondary structures, starting to unwound and lose the properties of it, right? So what we tend to usually do is we have an elastic network, almost like a rubber band, holding the structures together and forming a network. So we have a semi-rigid structure, which we allow to move over a period of time. Of course, because we're coarse graining it, we are limited to something called resolution limit. So instead of having an exactly oxygen from which phosphate interacting, we're going to end up with just 1 phosphate bead. So we're trading off resolution, but it's perfect for identifying a lipid binding site unbiasedly, which is our example I'm going to show here, which is the work done by George Hedger in Mark Sansom's group, where he's looking at cholesterol binding site in the protein. Right, so we have a cholesterol coming to one of the protein by randomly put cholesterol in the binding site. It will equilibrate itself and find a binding site on the protein. And here we can identify the residues which are making contact with it. And these has been shown previously to nicely identify the binding site. And it's not just cholesterol on this GPCR has been worked on. We have the Kier channel previously that putting PIP2 randomly in a box and it will find a binding site on a Kier channel. So it proved a very good technique to first identify the binding site of a lipid unbiasedly. And then in the next video, we'll be looking at how we can quantify binding free energy.